We are looking at pure n equals 2 SU2 theory in n equals 1 language. It's made up of one chiral multiplet in the adjoint, one vector multiplet, and you remember also that this theory has a moduli space. The moduli space is parametrized at least semi-classically by trace phi square, where phi was the scalar and the chiral multiplet. And going off on this moduli space was having expectation value for trace phi square. Therefore, at least semi-classically, an expectation value for phi. Therefore, induced spontaneous symmetry breaking down from SU2 to U1. Okay. Therefore, the low energy effective action was that at least semi-classically for a U1 gauge field, pure U1 gauge field with no charged matter. You remember that we wrote down the form of this semi-classical effect we wrote down the most general form that the effective action of a U1 gauge field can take, consistent with n equals 2 supersymmetry. And that took the form imaginary part of d4 theta, then there was a del f by del a times a bar, and there was plus d2f by dA square w alpha d2 theta imaginary part. This was our low energy effective action, and our goal was to find, how this f function varies as a function of our moduli space of our U-plane. Okay. Now, in the last lecture, we explained that we did not think that a single chart of such theories could cover the whole complex plane, because that would be inconsistent with the requirement that the kinetic term for the bosons, for instance, or the kinetic term for the scalar field, was everywhere positive. That and holomorphicity would make that inconsistent. Okay, so we decided to try something else. That is, we decided to try to cover it with two charts. Also, before that, we know the form of this f semi-classically, namely at very large A. Okay, so at very large A, we know the form of this f, and it takes the following form. This was classical plus the one loop part, which was I by 2 pi a squared log a squared by log. Okay, this we know by, if you like, by explicit computation, or from consideration of the anomaly of the U1R symmetry. Right? You remember this. Okay. In the last lecture, we also described in what sense we thought that it might be that this theory would be covered by different patches. Okay? The sense was this. The rough sense was this. The idea was that in one patch we use one set of A variables, and in another one patch we use one set of gauge fields. In another patch we use another set of gauge fields, and across patches, so we get another description, but on the overlap of patches, these descriptions are the same because they're related by electromagnetic duality. That was the basic idea. Okay? Now, our description of electromagnetic duality was completely without supersymmetry last time. And our first job today is to see how we can upgrade this description to a description consistent with n equals 2 supersymmetry. Okay. So, let's say that we will often use the notation del 2f by del a squared is equal to tau of a. Okay? That's sensible notation because del 2f by del a squared is what appears inside the im w alpha, and classically what we put there is tau, which you remember was I by g squared plus theta by 2 pi, whatever, some 2 pi's around. Okay, so this is like the effective coupling constant as a function of A. Okay, great. So we will often use this notation. So let's take this part of the action, the part involving the gauge field, okay, and write it in the following form. Write it in the form tau of A, W alpha, W alpha. Okay? Now, our first job is to perform electromagnetic duality, which is to perform some manipulation on this action. Now, you remember how we did it in the non-supersymmetric theory. We took the theory with f mu nu. The Lagrangian had f mu nu, but what we don't see with our eyes when we see f mu nu is that f mu nu's are not the basic fields of the problem. F mu nu is equal to, at least locally, d mu a nu minus d nu a mu. So then we turned it to a description where f mu nu was the basic field in the theory, and then imposed the Bianchi identity as an equation of motion that came from a Lagrange multiplier. That Lagrange multiplier was itself a gauge field. Okay, that Lagrange multiplier was itself a gauge field. And then by integrating out the f's, we got a new description. Okay, we got a new description for the, which had the same form in terms of the new gauge field as the original f mu nu, except the g squared went to 1 by g squared or something like that. Okay, great. Now we want to do the same. We want to do something. We want to do the same thing or something analogous here, but in the supersymmetric context. Okay. So notice the following. Remember that W alpha was equal to lambda alpha, and then you kept going, and then there was some there was f mu nu somewhere in this expansion. Right? Expansion with 1 theta and 2 theta bars had f mu nu in it. Okay. So this field here was the superfield which was the analog, the supersymmetric analog of f mu nu. Right? You remember we had this V superfield, which was the supersymmetric analog of A mu. And f mu nu could be written in terms of V mu with some covariant derivatives. Right? There were 3 d alphas acting on e to the power v. You remember that, right? Okay, so the main point to recall here, is that f mu nu is like the supersymmetric, W alpha is the supersymmetric analog of f mu nu, whereas there's another field, there's a V, which was the supersymmetric analog of A mu. Okay, great. So the fact that f obeys the Bianchi identity, okay, is a consequence of some supersymmetric equation. So the first question we're going to ask ourselves is, what supersymmetric equation has as one of its components the Bianchi identity? Okay, So now let's remember what constraints this W had. Firstly, of course, W was a chiral superfield, right? W was a chiral superfield because it had 2 d bars and 1 d. It was roughly this on something, right? So it was a chiral superfield, but because let's sorry, just 1 minute. Okay. Yeah. So what equation here? What equation for W? Okay, implements. So the claim. So a claim I want to make is the following: consider the imaginary part of d alpha W alpha. Okay, consider the imaginary part of d alpha W alpha. This thing is equal to 0. Okay. Now, roughly speaking, this comes about as follows. Okay, we had this e to the power minus v, or if this is a U1 theory, this is even simpler, it's just v, right? So we had, okay, so we can write a serious formula now. We had that W alpha was equal, this is the U1 theory, so it's very easy. So it's d alpha d bar squared on v. Okay, now suppose I act on W alpha with d alpha. Okay, so we get d alpha W alpha. This is equal to d squared d bar squared on v. Because d and d bar are complex conjugates of each other. This is a real field. Okay, and therefore the imaginary part of d alpha W alpha is 0. Okay. So now this was not an equation. When you wrote this guy, in terms of V, it was not an equation. It was triviality. But that's the nature of these Bianchi identities, right? If you write field strength in terms of gauge field, Bianchi identity is not an equation. It's a triviality. Okay? But when you don't write it in terms of a gauge field, the Bianchi equation looks contentful. As an equation of field strength, it's contentful. Okay? So this has the similar flavor. If we didn't know that W alpha was d alpha d bar squared on some real superfield, then this equation would not be a triviality. We just take the expansion of W alpha and components, work out what this equation gives us, and if you do this little exercise, you will see that that the term involving the f alpha beta, that term we will get an equation which is basically, the Bianchi identity. We'll get the equation epsilon mu nu alpha beta del nu f alpha beta is equal to 0. Okay, this is an exercise you can do for yourself just by taking W alpha, expanding it in components, and working out what equation this guy gives for f alpha beta. Okay? You would have to, yeah, it's not a difficult exercise. Is this okay?
So,
yes? Does this give non-trivial equation on lambda? I think probably not. So let's work it out. W alpha was equal to lambda alpha plus blah, 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 blah. Oh, maybe, yes. Now, this equation, d alpha was equal to del by del. Maybe it's Dirac equation. Yeah, let's see. This d alpha is del by del theta alpha plus sigma alpha beta dot theta beta dot theta bar beta dot, roughly something like this. Del mu, yeah, mu del mu. Right. So now let's act this on lambda, on this thing. This guy on lambda gives 0 because the lambda term has no theta. But this guy on lambda does not give 0. Okay? It in fact gives the equation sigma mu alpha beta theta bar dot del mu of lambda alpha. But this is basically del slash on lambda is equal to 0. So it's just a Dirac equation for the fermion. So it's interesting. Yeah, it's not crazy. You see, because what we have, lambda is the superpartner of a gauge field. Okay, and the gauge equation of motion somehow is built into here. Now you might wonder whether the coupling constant. Interesting. One sec. Let's think about that. Are you saying this was real? Could be. Could be that this was real. No, it doesn't look like. Oh. Okay, it's true that lambda. No, but it was a chiral. It was a chiral fermion in 4 dimensions. Fermions in 4 dimensions are not both chiral and real. Right. No. So you're saying maybe part of this equation? It's a good question. Okay, it's true we have to take imaginary part of this. What is a bit surprising is that the kinetic term for lambda what is a bit surprising is that the kinetic term for phi is non-trivial. So the bosons have a slightly less trivial equation of motion. Why is the fermion behaving so trivial? That is your question.
So is there only one theta bar, which integrate over d theta bar squared?
No. This is just a superfield expression. So, as a superfield, okay, what is true? Sorry. There's this term here. Then there's what Diksha is correct about is we have to collect all terms with theta bar. Now there was a term here with theta bar as well. And when we act with the del by del theta, that will get affected. Yeah, so this, I would have to work it out carefully. But I think what's going to happen here is that will be one of these auxiliary terms, which will know about the Kähler potential, for instance. So it's like some modified Dirac equation. Yeah, something like this. Okay, I don't know offhand. I would have to check it, but it's a good point. There are two contributions. We have the coefficient of theta bar will be 0, and you'll get something involving some auxiliary field. And the value of that auxiliary field you would only know once you included the kinetic term also. It'll be something like that. Right? So yeah, it was too much to expect just pure free motion, because the scalar is not moving purely free, right? Right. Yeah. So something like that. Excellent question. It would be great if If one of you could work this out, I could also try it for next. Okay, excellent. But so what we have here is this equation, imaginary part of del alpha W alpha is equal to 0. This is what we want to impose, and we want to do it in a supersymmetric way. Okay? Now, so how do we do that? Well, one way of doing that is to add the following term to the Lagrangian. Take imaginary part of d4x d4 theta Vd, okay, times dw, and add it to the Lagrangian. The dw is d alpha w alpha, you understand, right? Where Vd is a new real superfield. Because it's real, the imaginary part here acts only on the d alpha w alpha. Okay? And because we've introduced this new superfield in a linear fashion, integrating it out gives you a delta function that tells you that d alpha w alpha is 0. Okay? So the idea is just to imitate what we did before. Okay? The idea is just to imitate what we did before, but in this supersymmetrically sort of covariant fashion. Okay? So now let's look at the part with the gauge field. The action is tau of A W alpha plus this was imaginary and then this plus imaginary of d4x d4 theta, this d2 theta. I'm not writing d4x, right? That's obvious, but some terms are d4 theta, some terms are d2 theta, so we write. So d4 theta Vd times dw, and then do the path integral, ignoring the fact that w was constructed out of v's as d alpha d bar squared on v. Just treating w alpha to be an arbitrary chiral superfield. Okay? Is this okay? Fine. Now, the next step is as follows. Okay? The next step is to the next step is this. First thing we do is transfer this d to the v by an integration by paths. Okay? And the next thing we do, okay, is to use the fact that w was chiral. Okay. Because w was chiral, we have that d bar squared or d bar of w is equal to 0. Okay, this is the definition of w being chiral, right? Okay, so now in this d4 theta, there is d4 theta has this path that is d2 theta bar. Let's look at one of these d theta bars. Let's say d theta bar 1. This was d by d theta bar 1. Okay, but we can write that as d theta bar 1, d bar 1 plus total derivative. Right? Total derivative we ignore. So this was d bar theta bar 1, but the d bar does not act on the w because w was chiral. Okay? So effectively, the two theta bar integrals can be traded for two d bars acting on V dual. Okay? So now what does this term in the Lagrangian become? We have 1D acting on V dual because we had integration by parts, and we have 2 D bars acting on V dual. Is this clear? So can you see that up to some minus signs, this is going to become D alpha D bar squared V dual times W alpha. And now there's a key point, of course, that now it's D2 theta. Previously it was D4 theta, but we've absorbed, so this is something you might have worried about, right? If you involve a real superfield, Lagrangians involve D4 thetas. But kinetic terms for gauge bosons involve D2 thetas. So how is this operation going to work so that it involves a real superfield as a Lagrange multiplier and still produces a D2 theta term? And the way it's working is that the 2 of the d theta bars are absorbed into becoming d bar thetas, d bar alphas acting on V dual. Is this clear? We are assuming total derivatives are unimportant. Now let's say we're on a torus, we've got boundary conditions. We are assuming that there is no issue. Okay. Fine. So now we can just go. The original theory was obtained by, of course, integrating out Vd. But now to get the new theory, we integrate out W. But that's easy to do because W is just quadratic in the action. So that's an easy thing. And when we do that, we get very much like what we had before. We get 1 by tau A WD WD by completing the square. Okay, I'm not keeping track of factors of 2 and signs and so on. You can look at that in the Seiberg-Witten paper. Every paper by Witten, every factor of pi is correct. Every factor of I is correct. Even when he gives talks, he gives blackboard talks, he gives this 1 over I times 32 pi squared square root 2. It's all correct. I don't know how he does it. Okay. But since he's done it, we can focus on. On the other hand, this other great physicist whom I was once taught by, Polyakov, he would refuse to keep track of these factors. It's just distracting you from the physics. I won't keep track. So anyway, since Witten was one of the authors on the paper that all of you have on your computer, so you can look up the factors from there. Okay, we will not let you be distracted from the physics. Okay. Excellent. Excellent. So we've almost accomplished our goal. Okay? We've almost accomplished our goal, but not completely. Because you see, had we been just working in n equals 1 theory, this is fine. We would have got tau goes to 1 over tau. But we're working in the n equals 2 theory. And the thing that appeared behind the kinetic term of the gauge boson was closely related to the thing that appeared in the kinetic term of the scalars. So what's the deal? How come we've inverted tau? Isn't this sort of breaking n equals 2 supersymmetry? We've not touched the scalars. Isn't this breaking n equals 2 supersymmetry? And for this part, so now let's go back. So what have we accomplished? We found that our Lagrangian is equal to imaginary part of del 2f by del f by del a times a bar d2 theta plus imaginary part of 1 over del 2f by del a squared WD dual.
But doesn't this say that it's not the multiplets of W dual and E which are in the n equals to 2, but some complicated function?
Some complicated function, exactly. But to make sure that this is what's going on, we have to find that complicated function. For W.
Equation of motion for W alpha give relation.
Will give relations. This would be one way of doing it, I agree. But there is another way, we can just look at it and do it. Okay. Okay. So you see, the point is this, that when we write down a Lagrangian for some fields, in Lagrangians you're always free to do field redefinitions. So A is a coordinate in field space. I'm always free if I want to work with some other coordinate in field space. Just a change of variables in the path. Nobody can stop me from doing that.
Since you are integrating over that.
Since we're integrating over all fields, just a variable change in the path integral, perfectly fine. So, I'm going to ask the following question. Can I find a new A variable in terms of which this takes the old form? And there is a very simple answer. Okay. There is a very simple answer, and that's this. Let's use this notation that we'll get very used to soon. A dual is equal to del F by del A. Okay. Logically speaking, A dual is a function of A. It's a holomorphic function of A. Okay? Now, suppose, oh wait, I get my signs right. I hope there wasn't a minus sign here. Yeah, there was a minus sign. When you do this, it comes out with a minus sign. Okay, you get minus 1 over 2. Kind of Legendre, exactly. It's even simpler, as you will see. There's no Legendre function. It's just keeping your wits about you. Okay. Now, let us imagine that this thing gives us, so this is some h of A, let's call it, some function of A. Now, let's consider the function h inverse. Actually, we will need, because of this irritating minus sign, minus h inverse of A. At least locally, this is well defined. Okay? And the role of h inverse of A, of AD. You're right. H inverse of AD. The function minus h inverse. The acting on AD, the function of h inverse, this function produces A. So that's the way of representing A as a function of AD. Like obviously, A is equal to h inverse of AD. Obviously, I've just inverted this function. Okay, so this function minus h inverse produces minus A acting on AD. Okay, so now, go on. Louder.
Could you explain that again? I didn't get one.
Yes. Yeah. What I'm saying here is a bunch of emptiness. That's why it's confusing. It's almost so obvious that it's hard to say. But let me say it. Okay? It's just, yeah, you'll see. What we've got here is a bunch of fields. Actually, one field, A. Okay? And this quantity del F by del A, I'm just going to give it a name. It's AD. AD is some function of A. It's del F by del A. That much is clear? Okay. This function del F by del A, I've called HA. H is simply del F by del A. Okay, just so that I don't have to say, okay. Now, if I've got that AD is H of A, I'll call it A. If I've got AD is H of A, then clearly A is H inverse of AD. Okay? So, the function that will be of use to us will be this minus. The first round we can ignore the minuses. In your mind, don't give too much importance. Minus of H inverse of A. Minus of H inverse is a function which acting on AD gives you A. Okay? So now what I'm going to do is to change my thought process. Instead of A being the basic field in the problem and AD being determined in terms of A, I will treat AD as the basic field in the problem and let A be determined in terms of AD. Okay? Since we're doing a path integral, I can choose AD to be the integration variable. I have to keep track of Jacobians. Let me come back to that. The thing about this is all Jacobians in the end cancel. There are many Jacobians. There were Jacobians from this. There were determinants from this duality and so on. When you put everything together, the Jacobian, all those Jacobians and all these measures from this thing cancel. Okay? So forget about the Jacobians for a moment. Okay? So just change to AD as being your basic path integration variable. Now you can do that. It's just that wherever A appears, it should be thought of as a function of AD. Fine. Okay? So we've done nothing. But now, the great thing here is the following, that this term in the Lagrangian was imaginary part of AD A bar by definition d to theta, which is equal to minus the imaginary part of AD bar A. Because imaginary part of a term and imaginary part of its complex conjugate are minus of each other. So far nothing. But now, if we regard AD bar as a basic variable and minus A as the function of AD, as the new del F by del AD bar, del F tilde by del AD bar, then this has taken the same form that our original Lagrangian took. Is this clear? It's tricky to say because it's nothing. Okay, there are no manipulations. You just have to change how you think of it. Okay? Great. So now our basic variable is AD bar. Okay? A is a function of AD bar, and whatever A was as a function of AD bar, that would be del, there would be some function F tilde such that A was equal to del F tilde by del A bar, del F tilde by del AD of AD. Is this clear? So if you want, we can, once we know A as a function of we've got this minus h of AD, we can now integrate it. Okay, define the integral of this with respect to AD. And we can call this, if you want, F tilde. None of this will be important in it, but just so you know what's going on. F tilde of AD. Okay, and then we have A is equal to del F tilde of AD by del AD. Right? What? Minus is important because we are representing A as minus h of AD. H inverse. Okay. So, having done this, now let's go and re-examine the gauge boson kinetic term. Okay? Look at that. This was 1 over del F by del A del by del A, which was equal to 1 over del by del A of AD, which, by the marvelous theorem of calculus, is del A by del AD. But A itself was first derivative of F tilde. So this is second derivative of F tilde. So now, when we regard AD as the new variable, the Lagrangian takes the proper form in terms of some new F tilde. In terms of some new F tilde, but fine. Okay? That new F tilde might be very complicatedly, you have to invert this function, integrate to find this new F tilde. But it's an explicit operation. We're not trying to explicitly, find the functional form, but you understand what we have to do. Is this clear? With these two operations, we see now that this operation of performing the duality transform of the gauge field and shifting mental gears on your scalar field makes the new theory again n equals 2 invariant with some new effective F tilde, the F tilde that produces tau goes to 1 over tau. Is this clear? Okay. So, what is the net conclusion? The net conclusion is that we can do this duality in this n equals 2 covariant way, at the end of which the role of A and AD has been switched. Okay? You go to AD and A and maybe some minus. Okay? So under duality, the fields A and AD get interchanged with one another. That's the net conclusion. Is this clear? Okay. Excellent. Fine. So this is the operation we're going to try to perform. We're going to try to take these n equals 2 dualities and to try to patch up our moduli space with patches. In one description, we'll use one dual description. In the other description, we'll use another dual description. Okay? Now there will be points in this patching up place where the kinetic term in the first description will go negative. We won't use that description there. We'll use the new dual description to make sure that the kinetic term in that thing never goes negative. As long as we always have a description which is good, we'll be happy. Okay, this is the game we're going to play. Is this clear? Excellent. Okay, now let's go back and look at what we already know. We've got this U plane. Okay, with classically speaking this singularity where the gauge bosons go negative. There is one more thing there's one more thing I want to tell you. One more technical thing before we proceed to going towards the solution. The last technical thing I want to tell you about, not technical, but the last thing I want to tell you about is about central charges. Okay? You remember that in this theory, we had n equals 2 supersymmetry. Okay? And n equals 2 supersymmetry allowed for a supersymmetry algebra with central extensions. Do you remember this from months ago when we were studying the supersymmetry algebras? We found that Q with Q bar was P. But depending on the various dimensions, we could allow other terms to appear on the right-hand side. Okay? And if you go back to your notes and look at them, you will realize that in 4 dimensions, the central extension happened when we took Q with Q, or Q bar with Q bar. They're complex conjugates of each other. And the central extension went somewhat like this. There was a Q alpha I, Q beta j. Okay? And that could have a term which was epsilon alpha beta. Epsilon alpha beta times times Zij. Now, Zij in this dimension had to be antisymmetric. Since n equals 2, we can just say this in the following form: Q1, Q2 is equal to Z. Okay? And Z was a complex number. Okay? So you go, what? Why is it necessary? Well, Q's are complex. So, it would be very unnatural for Z not to be complex. But, you take the complex conjugate of this commutation relation, and you don't go back to yourself. Right? So, had you gone back to yourself, it would have forced Z to be real. But you don't. You go to, Q bar, Q1 bar, Q2 bar, alpha dot is equal to the Z bar. Right? Okay, excellent. So, this is an extension of the supersymmetry algebra that was allowed on general grounds. You remember that. It was allowed on general grounds. The question about whether it happens in a given theory or not, okay, the question about whether it happens in a given theory or not is up to that theory. Okay. But now you see in this theory, we claim we know the low energy effective action of the theory in terms of this F. So we know this low energy effective action. This is supposed to be the Wilsonian low energy effective action. So this gives us an effective description of the low energy physics. So in this theory, in terms of F, which we still don't know, but in terms of F, we can figure out whether this happens or not. How can we figure it out? We can figure it out by doing the following exercise. A, work out the transformations of fields that implement n equals 2 supersymmetry. The n equals 1 supersymmetry is the obvious one, the one that comes from superfields. But you can work out the transformation of fields that implement n equals 2 supersymmetry either by using the superfield formalism I told you about in the earlier class, or by doing trial and error. Look at the most general kind of transformation, plug it in, demand that it's an invariance. Okay? Take your action, work out the transformation of fields that implement the n equals 2 supersymmetry. Then, use the Noether procedure to generate a formula for the conserved current that implements this symmetry. So you get some conserved current. Then, compute the commutator by using Poisson brackets. Why are Poisson brackets enough? They're enough because we already have the exact low energy effective action. So after we've got the exact low energy effective action, we're only supposed to do classical physics. Okay? So using Poisson brackets, compute the commutator of Q1 with Q2. Okay? This is an exercise one can go through. I did this once when I was a student, I remember. It was a long exercise. Okay. This is an exercise one can go through. I'm not going to inflict it on you here. Okay? At the end of going through it, you get an answer. Okay? At the end of going through it, you get an answer. Okay? Okay? And Cyberg would quote the answer, so I'll write it down for you. A and AD you already know. What are NE and NM? NE and NM are the number of units of electric charge and the number of units of magnetic charge of your solution. Okay? So the way it comes about on the right hand side, you get some expression for Z, it's some total derivative, then you integrate that total derivative and you get a surface term. And NE is the surface term that computes the electric charge, the Gauss law electric charge. And NM is the surface term that computes the magnetic charge, the quote-unquote Gauss law magnetic charge. Okay? In this effective U1 theory, whether this theory has or doesn't have particles charged under charged under electrically charged or magnetically charged, that this Poisson bracket calculation doesn't tell you. But it says that if you have an excitation that has electric charge of any units of charge and magnetic charge of any units of charge, then the central charge is A times NE plus AD times NM.
A and AD were the field, right?
Were fields, exactly, were fields, but this is the constant value of the field at infinity. Because it comes from that. So it's the expectation value in the vacuum. Okay?
For the charge corresponding.
Say that again?
It's the asymptotic value.
It's the asymptotic value of this field. Remember, we've got a moduli space of vacuum. So a vacuum are labeled by expectation values of various scalar fields. Of one scalar field. Trace U squared. A was roughly the square root of trace U squared. Okay? But whatever it is, it's got some expectation value at infinity. Okay? That expectation value at infinity sets the central charge in terms of number of units of electric flux and magnetic flux. Is this clear?
So in the quantum theory, is Z like an operator or is it?
Yeah, you should think of it as a number because it's conserved in the sense.
It's operator, right? It's not like Z times identity on the wave function.
Well, it acts as Z is A dagger, which is a number, A which is a number, it's the value at infinity, times the electric charge, plus plus another number times the magnetic charge. Now, in the sense that electric charge and magnetic charge are operators, it's an operator, but no more than that. In each sector, it's a number. In each charge sector, it's a number.
So it's like a number operator?
It counts, it takes some linear combination of electric and magnetic charges. Okay? Note that A and AD are both complex numbers. In general, the ratio is not real. So it's some complex linear combination of electric and magnetic charges. Is this clear? Okay, excellent. So, Now, you may ask, what sets the normalization of any? Okay? Remember that in this duality operation, we are always working with U1 gauge fields. Gauge fields whose periodicity is 2 pi, for the gauge parameter is 2 pi. Okay? So, any equals 1 means with that convention of the gauge transformation, a field which has any equals 1 transforms like e to the power I alpha. So, any equals m, any equals any means that field transforms like e to the power I any alpha. Okay? And then because we've got quantized electric charges, magnetic charges are also quantized. And this is Nm in unit of that quantization, units of that Dirac quantization. So, any and Nm are integers and with clear definite meaning. Okay? Another way of saying why was our U1 gauge field quantized? Why was it U1 with 2 pi periodicity? Because it started life as an SU2 gauge field. And then the U1 gauge field is just the JZ component of that SU2 gauge field. So that SU2 gauge field was compact. So any U1 subgroup of it is compact with definite normalization if you keep your wits about you. Right? Okay, is this clear? So any and Nm are well-defined meaningful quantities, they're integers. And Z is equal to A times Ne plus AD times N. Is this clear? Any questions or comments about this? Okay.
So this Ne and Nm, I mean, when we do the calculation, appear as
Integral of F on, in fact, yes, integral of F at infinity and in fact, integral of F star at infinity. Okay? They appear as some total derivative, which you can then transform to these integrals at infinity. Is this good? Okay, excellent. Fine. Now, this sounds mathematically interesting, but is it physically relevant? You might think this has no physical relevance, since my theory here was a theory, my low energy effective theory was a theory of uncharged fields. I had a U1 theory with uncharged fields. For instance, within the low energy effective theory, Ne is just 0. Right? Everything had no charge. And you might, I don't know, maybe, okay. But remember that the UV theory was an SU2 theory. When you broke the SU2 symmetry down to U1, you did that at the expense of having two kinds of excitations. First, you had W bosons, because the Higgs boson gave you W bosons. The Higgs mechanism gave you W bosons. The W bosons are charged under the U1 gauge field. Okay? So they are charged under the U1 gauge field. And you might expect, certainly semi-classically, if you work it out classically, these W bosons are charged and precisely obey the BPS bound. If you compute the mass of a W boson classically, okay, it's the BPS, what do I mean by BPS bound? You remember in sectors where the Z is non-zero, mass was less than equal to Z. In this case, mass was less than equal to modulus of Z. And particles which saturate that bound are called BPS. You remember they appear in short representations of the algebra. You remember that, right? And the W boson precisely saturates the BPS bound. Okay? Moreover, that's for any. So, in the UV theory, at least semi-classical expectations would tell us that there exist particles, okay, that saturate with electric charge, that saturate the BPS bound with this Z. Now, great. What about magnetic particles? What about Nm? Actually, the same is true for magnetic particles. Because remember that what we have is an SU2 theory which is spontaneous, which is broken down to U1. Now, in an SU2 theory which is broken down to U1, we have solitons. Is this clear? One way of saying this, this, first you probably know this, right? This, the Toft or Polyakov or somebody's monopole solution is in SO3 or SU2 broken down to U1. Okay? And how do we see this more, more clearly? How do we see this in topology? Well, one way of seeing this is as follows. If you have SU2 broken down to U1, okay, if you have SU2 broken down to U1, then the vector that breaks SU2 down to U1 breaks it down to U1, but that vector itself lives on an S2 because it's an adjoint field. So it's a vector in space-time. It's got a non-zero expectation value. It can point anywhere in SO3 space. I'm treating SO3 and SU2 same for this. It changes a factor of 2 in some considerations, but otherwise doesn't matter. Okay, so that vector itself lives on an S2. So now at infinity, we've got some potential, let's say, or we've got spontaneous symmetry breaking. So we know that at infinity, our expectation value of the scalar field has some given value. But nobody can force me to make that expectation value of the scalar field exactly point in the 3 direction. In gauge, because all directions are gauge equivalent. In particular, that expectation value of the scalar field can wind. Now, infinity at fixed time. Remember, we're talking about configurations in Lorentzian space. Infinity at fixed time is an S2. So the set of all configurations are S2s that live on an S2 and so are labeled by winding numbers.
Does it take the expectation value, or for the finiteness of the action we have to demand that at infinity it becomes constant or something?
Well, the easiest way this happens is if there's a potential that fixes a particular expectation value. Okay? But in this case, as you say, if the expectation value were to change, we would get infinite energy.
Yeah, kinetic energy.
Okay, yeah. It's basically the statement of spontaneous symmetry breaking. At infinity, your field has to be frozen, except you can't phrase gauge modes because it's nothing. Right? So the fact that the field, the physical, anything physical you can build out of the field is just frozen at infinity is spontaneous symmetry breaking, and that happens, as you said, because if you had fluctuations at infinity, that costs infinite energy. Okay, great. Such a configuration is one of these solitons. Now you may wonder, that's great, this is a soliton, but why is it a monopole? I've got some scalar field, winding, looks like a matter soliton, but where's the monopole? The problem is this. You see, I've got this scalar field and it winds. And so now we can put the Chintan's criterion. Is this winding something that satisfies, that is finite energy? Let's check. Okay? We're in 2 dimensions. We're in 3 dimensions. Okay? So the energy is of the form del phi, the whole thing square. Suppose I'm winding, then my derivatives at infinity are going like 1 over r. Because the length scale of variation is r. Okay? So del phi sort of like 1 over r. So del phi square is like 1 over r squared, but I've got d3r. So this is infinite. And this is why, in a theory with just a global symmetry, even if global symmetry were broken, such winding configurations don't exist. But in a gauge theory, this can happen because you see, I wrote the kinetic term wrong. I wrote the action wrong. It's not del phi the whole thing squared, it's d mu phi the whole thing squared. So now one can try to arrange for the gauge field to also vary, so that d mu phi stays 0, becomes infinity faster than 1 over r, in fact like 1 over r square at infinity. If I do that, clearly I'm linking what the gauge field is doing to what the scalar is doing. Okay? And it is not difficult to convince yourself that that linking produces integral of B field is such that it demands that the integral of the B field at infinity, where B field is defined as B field in the direction of the local scalar field at that point, the U1 B field at infinity. Okay, B field at infinity is equal to this winding number of the scalar field. Okay, there are many ways of saying this. One way is a way we discussed before, by making this winding, happen only on a little patch. Making this winding happen only on some little patch, and then that patch then requires some gauge, some non-trivial gauge thing. Anyway, you can look at it. By the way, I should have said this. You see, there is the danger. There is another danger. The danger is I take the gauge field and I make it something non-trivial at infinity. And then I may have got rid of the infinity from the kinetic term of the scalars, but I might get an infinity from f mu nu f mu nu. So what we want is that the gauge field is not just 0, but it's pure gauge at infinity. Okay? And that combination links that pure gauge flux to this winding number. Okay? Again, if you want to read about this, it's beautifully described in Coleman's book, Aspects of Symmetry. Beautifully described. Okay? But okay, this was a quick lightning review of this. So, in addition to these W bosons, which semi-classically exist, these magnetic monopoles also semi-classically exist. Moreover, these magnetic monopoles are BPS. Also, again, a calculation you can semi-classically do. Okay? So, semi-classically we find that the theory has these W bosons, which are BPS, and has these Topol-Yakov monopoles, which are also BPS. Okay. Now, question, do these particles continue to exist beyond semi-classics? Do they continue to exist at finite A? Is there any way we can answer this question? Finite value of A, or finite U square, not very large U square. Very large U square, we're pretty sure that they exist, right? Because semi-classically they exist. What about finite values of U square? Do they continue to exist?
That shouldn't change.
Gone?
Yes, Z should not change.
Yes. Z changes only because A and AD change.
If it's non-zero, then it should remain.
Well, sorry?
If it is non-zero, it should remain non-zero.
If Z is non-zero, it should remain non-zero. Good. Before analyzing Diksha's comment, let me make one more statement. The fact that Z for electric particles is proportional to A is something you know. Because in the Higgs mechanism, when you have del mu, d mu phi, the whole thing square, okay, when you have d mu phi, the whole thing square, and you get an expectation value of phi, the mass for the gauge boson is A mu squared phi squared. So the mass square for the gauge boson, mass squared is equal to phi square, or mass is equal to phi. But A was phi. Okay? So semi-classically, this formula agrees with not only the existence of these gauge bosons, these particles agree with semi-classics, because this formula itself agrees with semi-classics, as of course it had to. Is this clear? That this formula, I've just thrown it at you as a statement saying you can derive. But it's a very intuitive formula. Because this is just the mass of a W boson, at least semi-classically. What about this guy? Semi-classically, F was equal to tau A square by 2. Okay? Classically, semi is too strong for this. Classically, F was equal to tau A square by 2. Therefore, AD was equal to tau A. Remember, we decided we would always work with conventions where theta is switched off. Theta is 0. So AD, tau was 1 over g squared times some number. Okay? So AD was equal to 1 over g squared times A. Okay? And this again agrees with your semi-classics. Because a magnetic monopole is a soliton. So it has a mass 1 over g squared because it's a classical solution. And its mass is set by the only massive parameter in the problem, namely the expectation value of the scalar field, which is A. Okay, the energy of a soliton is 1 over g squared. So its mass is 1 over g squared times A. So semi-classically, this agrees with what you expect from semi-classical ideas. And of course, the numbers also, if you do them more carefully, also agree. Okay, so this Z being the mass of a BPS particle and the statement W bosons and solitons are BPS all makes a lot of sense.
So why should we expect Z to be a mass of some?
Because of the BPS bound. The BPS bound, you remember, was the statement that masses of particles were greater than equal to Z. Okay.
That came
From supersymmetry algebra.
Yeah, that also came from applying Q twice, and that goes to.
Yeah, that comes from applying Q twice. They won't be the same Qs. There would be a Q and a Q dagger because you have to get energy into the game. Okay? But just that algebraic consideration told us that mass was greater than equal to Z. And you remember that when mass was equal to Z, particles appeared in special short representations. Okay? And semi-classically, that is true for Z bosons. And in fact, also for monopoles. So you should expect that the Z bosons, the W bosons and the monopoles are BPS. Certainly they have mass bigger than this. That was a theorem. But the masses are saturated semi-classically. How do we know masses are saturated semi-classically? One simple argument is this. You see, if the W boson, if the W boson was a generic long multiplet, then we would have plenty of states. But you just look semi-classically. We are working in a theory with one scalar field, two adjoint fermions, and one gauge field. You do the Higgs mechanism on the semi-classics, you'll get some multiplet with some small number of fields. Okay, by just comparing number of fields with the tables that we looked at when we were working out representations in Strathady's paper, you'll immediately conclude that this has to be a short representation. Okay, it's a little more complicated to make the same argument for the solitons because you have to look at zero modes, fermionic zero modes. It's a little more complicated, but not much.
How it is getting enforced that we are working in this extreme case? Is it a choice?
The BPS?
BPS?
No, it's not a choice. Semi-classically, it's true, right?
Okay. Yeah.
You can check this in two ways. A, you can compute the mass of the W boson, which we've more or less done, right? It's 5 squared. And compare with the BPS bound. This is one way. Second way, you can just check the representation that the W boson transforms in.
Yeah, that I am understanding that this is the BPS case.
Yes.
But how it became that special case?
Why did it become BPS? It became BPS because these W bosons started their life as massless gauge fields. Remember, massless gauge fields were in short representations of the algebra.
And you don't change.
Nothing discontinuously changes. right? So short representation becomes continues to a short representation. Okay, and that's how it worked. It's a bit more complicated to argue for the solitons. Bit more complicated to argue for the solitons because you have to work out what representation it appears. You could wonder, solitons are bosonic objects. Where are the fermions? Turns out that the solitons have zero modes, fermionic zero modes. Okay, and the quantization of those zero modes gives rise to a multiplet of solitons. And that multiplet that you get from quantizing these zero modes is also a short representation. Another thing you can check. I'm not going through all of this here because that would take us way away. Okay, if you want to read more about this, there are these lecture notes by Harvey in TASI 97 about instantons, solitons, dions. Very nice. A very good place to read more about the marriage of supersymmetry and solitons, marriage of instantons and solitons, marriage dions and supersymmetry. Sorry, marriage of, sorry, very little, not so much about instantons, mainly about the solitons and the dions. Very nice lectures. Okay? Excellent. But the net conclusion here was the following, that these mathematical formula here is physically relevant, at least in the semi-classical theory. It's physically relevant and it describes, at least semi-classically, solitons and W bosons. In fact, there are also these things called dions. We'll talk about that later. We'll talk about dions later. In fact, that I might do some more serious discussion of these dions. Okay, but fine. There are the solitons. There are the magnetic monopoles. There are the electrically charged particles, and at least semi-classically, these guys exist. Now, can we argue that these objects continue to exist, not just semi-classically, but over some finite range of A? Now we come back to Diksha's argument. I think more or less what Diksha wanted to say was something like this. Look, suppose I've got, let's say, a W boson. Okay? This W boson is a particle with, in some short representation, the number of fields associated with it is some small number. Okay? It's the lightest state with charge 1. Now, if as I vary parameters, say I move along moduli space, this W boson were to suddenly become non-BPS. First, if the W boson is BPS, of course, it's the lightest state in the problem with that charge. It's stable. Now, as I move the parameters of the problem, let's say I move in moduli space, perhaps you might wonder whether the W boson could suddenly become non-BPS. Perhaps this could happen. But if it did that, it would have to suddenly, its multiplet length would have to suddenly jump. So the set of lightest charged particles in this theory, instead of consisting of, 2 scalars and 3 fermions or whatever it is, would now have to consist of 8 scalars and 10 fermions or whatever it is. Because it would have to go from a short to a long representation. Okay? And that would seem utterly unreasonable. In fact, impossible, right? In fact, impossible, because it would tell you that the spectrum in the charge, in the sector with charge 1, is jumping discontinuously. Because you see, earlier, before, when it was BPS, we had a certain number of particles. Then you might worry, what about things with What about particles with, I don't know, charge 2 or charge, two charge 2s and one charge minus 1 or something like that? Maybe you can make a bound state of those. Okay? But now, these are particles. The spectrum of multi-particles is just sum of energies of particles. So there's a mass gap, these are massive particles, a mass gap between this guy and those higher guys. Okay? So for the number of states in this charge sector to jump suddenly like this, okay, sounds at least unreasonable and maybe just plain inconsistent. It's not totally clear it's inconsistent because there are the massless fields in the neutral sector, and perhaps you could have some of the massless states disappearing to make this, but how would that happen? Anyway, it doesn't sound very easy for this to happen, right? Is this clear? The kind of argument I'm trying to make is a less precise version of the argument we made with superconformal indices. There the arguments were very precise. We classified all short representations, all long representations, combining. Here these arguments are a little less precise because we're working in some theory which is on R3. There's a continuum of long wavelength massless modes. It's all a bit less precise. But anyway, it seems unreasonable that this jumping happens. Because your spectrum of of charged particles would have to just suddenly and discontinuously change. And how would that be consistent with continuity of physics? That's the idea. Okay? Great. So this argument motivates you to expect that these BPI's particles exist all through, at least in some range. Now, suppose you had a BPS dion. So particle with charge 1, electric charge 1 and magnetic charge 1. What about that guy? So this argument that I made for the W boson would also apply for the soliton. But suppose you had a BPS dion. As we will see, semi-classically we have BPS dions with charge magnetic charge 1 and electric charge n for all values of n. Okay. Suppose you had this BPS dion. What about that guy? You know what a dion is, right? It's something which has electric and magnetic charges. I'll tell you more about dions next time. About how semi-classically you know dions exist. I'll tell you about that. Since you're probably not very familiar with that. Okay, but suppose we had a BPS dion. What about that guy? Well, the same argument works except if AD and A become parallel to each other on the complex plane. You see, the mass of a BPS dion would be A plus AD. Now, A has some real number. This is real A times e to the power I phase A. Let's say that we're looking at the dion with electric charge 1 and magnetic charge 1. Okay? So this is expectation value of real A times e to the power I phi plus expectation value of real AD times e to the power I don't know, chi AD. Now, this is of course less than equal to RE, A, not real, but magnitude, what is it called? Length. What is it called? Value. Mod. Okay, this is less than equal to mod A plus mod AD. When is equality saturated? When the phases are parallel, are equal. When the phases are equal, you can take the phase out. Mod of phase is 1. And this just becomes mod A plus mod AD. So if the ratio of AD and A becomes a real number, in that situation, now you can have this dion, you can have this dion suddenly ceasing to exist. Because you see, what you could, at that point, there was a continuum. There was the two-particle continuum of one monopole and one electron, which had exactly the same energy as this dion. Right? And then there's no argument that tells you that when you go through this point, that this dion should continue to exist, because it could just continuously move into the continuum spectrum of the monopole and W boson. And indeed, in several areas of physics, this is known to happen. That you've got, in some area of moduli space, you've got a dion, and then there's a boundary in moduli space. It's called a wall. Okay, there's a boundary in moduli space where the mass of the dion becomes equal to the mass of a monopole plus the mass of a W boson. Where the mass of the dion was less than the mass of the monopole and W boson, our same argument tells us that it should just continue to exist. But then when it becomes equal to this, as you go across the wall, it can and sometimes does happen. Okay? That the dion which existed to the left of the wall no longer exists to the right of the wall. So to speak, it's decayed into the monopole and the W boson. Okay? So, regions where, and everything I said about this dion will apply also to dions with, let's say, magnetic charge 1 and electric charge n. Can decay into one monopole and n W bosons, or similarly more complicated dions. Okay? So, our expectation is the following. In this moduli space, the spectrum of dions should be the same as we have semi-classically, until we reach a wall in this moduli space. Okay? The wall is defined by A by AD becoming real. Okay, this wall, so we've got this moduli space here. And we've got some region, let's say some region here where A by AD becomes real. The spectrum here can be discontinuously different from this, of PPS states can be discontinuously different from the spectrum here. But everywhere here should be the same, everywhere here should be the same. Of course, the masses depend on A and AD. But the existence of these particles should not change. This is the expectation. Is it clear? Is the logic clear? Okay? Now, excellent. Excellent.
How do spaces, let's say phi goes to 2 pi, phi changes by 2 in the values.
Yes.
And then you have again same condition coming.
But
the boundary identified?
well, as long, if phi, anywhere where AD by A is real,
Okay, you are putting a boundary.
there's a boundary. Nothing else matters. Okay? Now, motivated by this argument, this is how we're going to proceed. We'll stop soon. We'll do the mathematics next class. Okay, I've been trying to set up the conceptual framework. Next class, we will try to get to the solution of this problem. Okay? Motivated by this discussion, this is what we are going to try to do. Okay. What do we know now about the problem? We've got this U plane. Okay, we've got this U plane. And on this U plane, we want to find such a description at every value of U. So, one way of thinking of this problem is to think of A and AD both as functions of U. Semi-classically, the relationship of A to U is A square root of U. Quantum mechanically, inside it's just some function of U. Think of A and AD as both as functions of U. Okay? And we've got this U plane, and we know everything that's happening far away. Now, let me give you just a 5-minute appetizer for what we're going to do in the next class. We have argued that it's okay that if we go around some singularity in some description, some singularity, let's say in the U-plane, the theory comes back to itself up to a duality transformation. This we have argued. Okay? In the next class, we will examine the set of all duality and one more trivial transformation in some detail. Find that the set of these transformations are SL2Z. Okay? So we will allow ourselves to have singularities of this U-plane and allow the nature of these singularities to be monodromies in this description that lie in SL2Z. Okay? In fact, there is already a singularity at infinity. And that singularity we saw from F1 loop. I will explain that to you. The singularity came from the fact that F1 loop had a log. And when you have a log of A, and A goes around 2 pi, something changes. So already there's some monodromy at infinity, even semi-classically. That is a relatively trivial monodromy. It corresponds to the monodromy you get because theta goes to theta plus 2 pi. Okay, we will discuss that in detail. Okay, now we've got this. We know that if we go around infinity, we've got some monodromy. Which means that on this U-plane, there must be some other singular regions. Classically, that singularity was at 0, where the gauge bosons were massless. Quantum mechanically, we're going to guess that that is not what happens. Okay? Quantum mechanically, we're going to guess that that is not what happens. Quantum mechanically, we're going to guess that there are singularities associated with other kinds of physics. Okay. If you remember, we had this Z8 symmetry, which acted like Z4 on phi, because phi was charge 2, and therefore acted like Z2 on U, on phi, trace phi squared, so U. So on this U plane, we have this Z2 symmetry. So if there's a singularity at one point in U, there's a singularity at another point. Okay? So we're going to guess that the singularity doesn't appear at U equals 0, but somewhere else. And then that ensures that there must be two different singularities. Now we're going to guess that the first singularity, motivate, you'll see, is associated with a monopole becoming very light, or effectively massless at this point. Which means AD going to 0. Okay? And we're going to guess that the second singularity, you'll see why, where these come from. That the second singularity comes from a dion becoming very light. Okay? Which means A becoming AD or A becoming minus AD depending on conventions. A charge 1, 1 or 1, minus 1. That's a little bit convention dependent. A dion becoming a massless. Okay. Next, we will verify our guesses by this calculation. If a monopole becomes massless, if we go to the frame where the monopole is the charged particle, the duality frame where the monopole is the charged particle, then a monopole is just some standard object. And we can compute the contribution of the monopole to the prepotential by doing a one-loop calculation. Okay, the contribution of this in that frame. But since we know how to transform between frames, the calculation we do is we get an answer. That answer will allow us to calculationally compute the monodromy around this point. Similarly, we go to the frame where the dion is the charged particle and do the same calculation. and we are able to compute the monodromy around this point. And one of the first pieces of evidence that this is the right picture is that the monodromy that we know from semi-classical physics matches the monodromy we get from assuming that a monopole has become massless and assuming that the dione has become massless. You'll see how these words get translated into formulas. Okay? So, this is what we're going to then propose. That there are 2 points on this moduli space which, by some choice of coordinates, we will call 1 and -1. Have to be minus each other because U goes to minus U symmetry. There are 2 points on this moduli space where there are singularities. And our effective description has this semi-classical monodromy which breaks up into these 2 monodromies whose non-abelian product, whose product, but these are not commuting monodromies, okay, equals this thing. Okay. Then,
What do you mean by non-commutative?
Non-commuting, which means this. Suppose I have, a monodromy is an element in SL2R, SL2Z. Okay? So, either you have 2 elements of SL2Z which commute with each other, or you don't, just the same element maybe n times.
How to set the ordering?
We'll see. Yeah. We will explain that. Okay? Now, these 2 different monodromies, we will have this calculation that sets up this picture. Now, once we have this picture, we now know what mathematical problem we want to solve. The mathematical problem is to try to find f of a, chart-wise, that has the property that it has these monodromies. Okay? And the way we're going to solve it is as follows. We're going to realize that this SL2Z problem can be solved by associating a torus with each point on this punctured complex plane. A and A dual will be the lengths of cycles of this torus. And tau will be sort of like the tau parameter. Again, we will see. Okay? Now, our tau parameter being positive was the condition from physics. And what's happening is this torus, as we move around, sort of rotates. So tau can go from positive to negative, but we can always make an SL2R transform. So we go to a new cycle such that tau is positive. Okay, so that's going to be the picture. That we have a torus at each point on each point of this U space. And some geometrical quantities, we'll look at all this in detail. Some geometrical properties of the torus will give us A dual, this F, blah, blah. Okay? The great thing about this is that we can set it up in this language to make sure that there is always a frame in which d2f by d a squared is positive. This geometrical picture will ensure this. Okay? And then once we've set it up in this geometrical language, the idea of that it's a fibration with a base space and a torus on top of it, for the tori have given monodromies, then this mathematical problem of how to make this vibration has basically a unique solution and can be solved. And we will then eventually just find this f of u. This is our goal. Okay? But it will come from the basic starting point is this picture with the puncture. These monodromies. And then it's turning the cranks in some mathematics. Okay, fine. Next class we will try to get more quantitative and get our hands dirty in actually solving things.